Ideals in a ring R are analogous to normal subgroups in a group. I'd like to expand on that idea more in this video. So if you have an ideal of a ring R, you could form the factor ring or the quotient ring R mod I. It's a set of cosets. Same thing that we've seen for groups. And this set can have an addition defined in the way that you might expect, and a multiplication defined this way. So the first theorem I'd like to prove is that the factor ring, the set of cosets, with this addition and this multiplication is indeed a ring. So the addition and the multiplication satisfy the conditions needed to be a ring. So for the proof, I can get away with remembering that R with plus is a group. It's an abelian group. So since it's an abelian group and I is a subgroup, R mod I is a factor group if I only think about addition. We've proved all the necessary properties that factor groups satisfy the definition of group. The only thing new here is the multiplication. So because factor groups are groups, we only need to check that the ring multiplication satisfies the needed properties. What are the needed properties? Well, the first property is that the multiplication needs to be well defined. The second property is the multiplication needs to be associative. And the third property is that the multiplication has to interact nicely with the addition. So the distributive laws need to hold. These are relatively routine to check, so I'm not going to check all three properties. I'm just going to check the well-defined property, and I'll leave it to you if you decide to check associative and distributive properties. So I'll just do 1/3 of the proof. I'll show that the multiplication in the factor group is indeed well-defined. So let's do the well-defined. To do that, I can take different representatives in the rings. So let's suppose I take A prime in the first coset and B prime in the second coset. What that means is the A prime is equal to A plus I, and B prime is equal to B plus J for some I and J in my ideal. Okay, then what do we have? Then I'm going to consider A prime, B prime plus some K. This K here, I want also to be in my ideal. So A prime, B prime plus K, using what I know about A prime and B prime, can be written as A plus I times B plus J plus K. Now all the distributive properties hold. These are just elements in my ring R. So I can expand everything and get AB plus AJ plus IB plus IJ plus K. Now, all of these terms here, I claim, are in I, my ideal. The definition of ideal says, if I take anything in my ring, if I take any A in my ring and multiply with anything in the ideal, I get back in the ideal. So multiplying by something in the ideal always lands me back in the ideal. So this is in the ideal, this is in the ideal, ideal. I could add two things together, get back in my ideal. So all this is in I. So this whole element is in AB plus something in my ideal. What I've actually showed was, I've actually shown that A prime B prime plus something in my ideal lands back in AB plus I. I could show reverse containment, so this shows one subset containment. Reverse containment is similar. So what I actually get is A prime B prime plus I is the same as AB plus I. That actually verifies the well-defined property. Okay, so we have factor rings are actually rings. Let me end this video by making a definition that I think should be somewhat familiar. So rings R1 and R2 are isomorphic, and that's denoted R1 isomorphic to R2. If there is a bijective homomorphism, a bijective homomorphism phi that goes from R1 to R2. Okay? By the way, when I say homomorphism in context of rings, it's implied that I have a ring homomorphism. So the function phi splits over addition and multiplication.